What I'm presenting today is a result of an ongoing collaborative effort. The slides and the case study have been elaborated together with Laetitia Saoud and Jean-Luc Voirin from Thales. And what I am presenting today is a result of 1 or 2 years of brainstorming, development, and so on. So it has involved developers, mainly from Thales, and I would like to mention Felix Dorner, and also from Altran in the context of the Clarity project. But it has also involved operational engineers, mainly from Thales, but also from Ariane Group and some other organizations. When we study the literature regarding modes and states in systems engineering, there's no consensus that emerges for what is exactly a mode, what is a state. Sometimes people understand them differently. So I will first try to explain our interpretation of what is a mode, what is a state, and so on, in the context of the Arcadia method. A mode is a behavior that is expected from the system or from a component in chosen conditions. So if I take the example of a drone, the drone can be in autonomous mode, it can be en route, it can be on zone, remote controlled, silent, communicating, and so on. So these are all contexts of operation that are planned and that are part of the capabilities of the system. A state is a context that is undergone by the system or a component in specific circumstances. Sometimes these circumstances are imposed by the environment. The tank can be half full. We can have night and day, different combination of sensors, not necessarily chosen, but this is something we have to cope with. And this is the main difference we do between modes and states. A situation is a combination of states and modes at a given instant. So for example, we might have different phases in the missions. The system might have different modes, for example, autonomous or remote controlled. And then each of the subsystems might have their own state machines and mode machines. So what we call a situation is really one given context selecting the current mode or the current state in different modes or state machines. A configuration is a set of system parts or capabilities or functions that are globally available or unavailable in one given mode or state. So for example, reconnaissance or localization of targeting capabilities and so on might be available or not, depending on the current mode or the current state. So we'll see how we will use the configuration concept to specify the impacts of modes and state on the architectural design. Later in these slides, you will understand why this box is red on the left and kind of greenish blue on the right. So what are we trying to do here? Our systems are, of course, more and more complicated, and what we are expecting from the systems is also more and more complex. So what we are trying to do is to understand how the system will behave in specific situations. Situations being a combination of states and modes. We want to be able to predict or anticipate the system behavior. We want to be able to compute or to perform non-functional analyses in different situations. So this is basically the problem we are facing, and the problem that our systems engineers, when they write their design documents and so on, struggle to capture. So I will start with the methodological approach, and then I will illustrate it with a use case. The methodological approach has been the most difficult part and the biggest achievement of this effort. We knew how our systems engineers were working, basically doing matrices and tables, establishing correspondences between modes and states and relating them. We implemented the concept of configuration to help our systems engineers specify what was available in one given mode or one given state. And we gave them a prototype. They played with this prototype, adding the configuration concept to Capella during about 1 year. But the experimentations were not really satisfying. We were not able to put on our finger on what was missing in the articulation between the concepts of modes, states, and configuration. Until one day, in the middle of a brainstorm, we kind of saw the light and saw that what was missing was the concept of configurations. So back on the methodological approach. So everything starts with modes and states. We introduce the concept of configuration to specify what is available in terms of functions, components, interfaces in one given mode or in one given state. We could do that directly from the modes or from the states, but introducing a new concept, the concept of configuration, gives us the opportunity to optimize the specification, because several modes can share the same configuration, the same set of elements that are available or not. In the Capella diagrams, we are now able to preview the impact of one given configuration on any component. In this example, on the top we see an hybrid SUV, which is in combustion mode, and all the elements that are not part of these configurations are grayed. In the bottom, this is the opposite. We visualize the electric mode, and then only one component is grayed. So we specify atomic configurations that describe what is exactly available or not in one given mode or one given state, and we preview that in Capella diagrams. Then we have the concept of situation. A situation is an expression that selects a set of current modes or states in different modes and state machines. This is illustrated here. My situation is I am in mode A, and I can be in state D or E, and I am in mode G. Mode A can be for component 1, mode G for component 2. So we have a situation that describes one given context that I will use as a prism to study my architectural design. Based on this situation, and based on the atomic definition of what is available for each mode or each state, the tool is able to merge the atomic configurations and compute a global configuration that specifies what is present, what is not. Here, we can sometimes detect inconsistencies, because in one mode I've specified that one function is present, and in another one I've specified that the function is not present. This might be a specification issue. This might be an architecture issue. So we can rework it until we reach a satisfying global configuration. On the other side, we can also use the configuration concept to express the expectation we have from the system in a specific situation. Here, we would rather associate functional chains and scenarios to this configuration of interest. And what we want is to make sure that these functional chains and scenarios can be played entirely in one given situation. So to do that, we are going to compare this global expected configuration of interest and the global computed configuration that is the sum of all the atomic consequences of each mode and state that is part of the situation. So this is the general frame of the approach, and this is relevant for system, actors, components in any Arcadia perspectives. We can conduct the same kind of approach in system need analysis, logical architecture, or physical architecture. The principles remain the same. And what we see on the slide is really the complete approach, but it is really possible to have only a partial application of that. Some projects will only care on working on the consistency of the atomic configurations, and some others will maybe not associate atomic configurations to their mode and states and will only have global configurations of interest to capture what is expected by the customer, for example, in specific situations. So we can have partial applications of this approach. What you see on the slide is a lot of flashy colors. They have a purpose. They will help relate the method steps in the case study that I'm going to explain now. So the case study is a small nano satellite that is dedicated to the measurement of environmental conditions that are undergone by the payload. They basically try to measure the deteriorations of hardware components that are sent in the space environment. So it's a simple system that covers measurement activities, capabilities to control the spacecraft, and of course, communications. These are the main capabilities of this simple system. Our goal is to support system specification elaboration and help analyze its consistency. It's to support the architecture early validation, and in the space domain to support fault detection, isolation, and recovery. So first, I will really focus on the system specification, so the system need analysis in Capella. So everything starts with modes and states. We have several mode machines and state machines, so there's nothing new here. We have the system modes, so the system modes are fail-safe, detumbling, safe mode. When the nanosatellite is operational, then it can be nominal without communication, in experimenting on no current experiment, or the satellite can be in eclipse mode. We have states for the environment. Is the ground visible from the satellite, or is the ground not visible? Is the sun visible from the satellite, or is the sun hidden? And we also have the system phases that we specify using modes. So there's the launch, the transfer, then the satellite is in orbit, and then it's deorbiting. So there's nothing new here. This is pretty standard. We can associate transitions to functional elements and so on. Like this is all things that have always been available with Capella. You can exploit these modes and in these states in Capella sequence diagrams or interface diagrams and so on. So the same, nothing really new here. What is new starts here, when we start to introduce these configurations. Configurations can sometimes, or maybe most of the time, be mapped in a one-to-one relationship with the modes and states. But not necessarily. As I've said a bit earlier, different modes can share the same atomic configuration, meaning the same setting of the system, the same availability of components and so on. So for the satellite, I give a few examples. The ones that are related to energy, the satellite can be sun-powered or self-powered, like working on a battery. And when it comes to communication, communication can be nominal, degraded, or no communication at all. So these are atomic configurations that we specify with this in this small example. Now I'm going to play a little bit in the tool to show you what a configuration looks like and how we can preview this configuration in a diagram. So the first thing is a table that allows to specify the content that is expected in one given configuration. So each column is the specification of one configuration. We can also see these or specify that using a dedicated dialog. So I can do that here. We see that the configuration can include functions, functional chains, component ports, scenarios, or any kind of elements. And we can define a configuration either by inclusion or by exclusion. By inclusion means I need to explicitly specify everything that is part or that is available in this specific configuration. If I'm using the exclusion approach, then I just need to specify what is not available in one given configuration. Then I can display one diagram. So this is a SAB, System Architecture Blank. And I have a new section dedicated to visualization of configurations. So I can select this tool, come here, and select the configuration that I want to see on this diagram. So the no communication configuration here specifies that these three functions are not available. And it also specifies that uplink and downlink connections with the ground control are not available. And we have also specified that each of the ports of the functions that are going or coming from the ground control are not available. So we have really the means to go pretty deep in the specification of what is available or what is not available. So basically, with this atomic no communication configuration, we have excluded all the functions that are establishing the communication, and we have excluded all the connections to the ground. I can continue with visualizing different atomic configurations. So for example, sun powered. So this means we can see the sun, so we receive energy that we need to convert in electrical power, and we need to store this electrical power for when the sun is going to be eclipsed. And then I can select the other one, the self-powered, and we can see in that case that the convert energy and the store functions are not available. Okay, so we have modes, we have states, we have defined atomic configurations with availability of certain elements, and then we can use a dedicated table to relate these atomic configurations to specific system and actor modes and states. In the simplest case, you would have one configuration per mode or per state. In some cases, you can have a little bit more complex combinations if you want to optimize the specification. On one diagram, I can also see different configurations. So I'm going to do that here. I'm going to display the no communication and self-powered or sun-powered. I don't remember which one it was anyway. So this is what is presented by default. We see the two now here. So here are the two configurations that are currently being previewed on this diagram. So this one is because of the sun-powered, and the three ones and the exchanges because of no communication. We have an option that allows to visualize the settings where we have ambiguities. I'm going to change the setting in Capella. So it's here, mode state preferences, and mark elements where we have conflicts. So now I'm going to select here both self-powered and sun-powered. So these are two configurations that are not supposed to happen concurrently. And now the functions where there's an ambiguity, meaning that it is included in one configuration and excluded from the other, are displayed in orange. So this was what I just showed. So now we had modes, states, atomic configurations. We can now think in terms of situations. In this situation, I can be interested in what happens if I am self-powered and with no communication. Then a validation would show that no problem, the different configurations don't have errors. Another one would be a situation where the satellite is currently performing the experimentation, but it is degraded, meaning that it doesn't have communications. In that case, we have a contradiction between what is necessary for experimenting and degraded specify that the communication is not available. So the result of this validation here would be there are errors in this setting. I need to be honest here. This comparison, the algorithm that we use for this comparison, are currently really basic. So the maturity of this part is not as good as the one we are aiming for. But I will explain where we exactly are at the end of the webinar. So now I switch on the other side of the approach, and I am discussing, for example, with my customer, and is giving me his requirement, and I will do global configurations of interest to capture them. So for example, I will express in terms of functional chains and scenarios what is expected in certain circumstances. So for example, expected configurations would be I need to control the spacecraft in orbit. I need to perform some standard operations when the satellite is in orbit. I need to exploit the solar energy. I need to experiment, and so on. And for each of these global configuration of interest, I will use the same definition table as we had previously for the atomic configurations. But this time, I will most likely associate functional chains or scenarios to these configurations. So if I preview what corresponds to the exploitation of solar energy in my architecture diagram. I have 3 functional chains. If I switch to the in-orbit spacecraft control expected configuration, then I will have 5 functional chains. So I'm going to display them on the diagram. Insert, remove functional chains, and I want downlink, uplink, thermal control, attitude control, manage modes and states from the ground. So now we see all these functional chains contributing to one specific expected configuration. And then what we want to do is start comparing the global configuration of interest and the atomic configurations. So for example, if I select the no communication atomic configuration, well, we clearly see that the absence of the unavailability of these 3 functions is having an impact on the functional chains that were included in the expected configuration. So this is when I compare that on the diagram. I can also directly compare these 2 configurations. So this time I will do it in the tool. So what I want to see now is a comparison between the expected configuration in orbit spacecraft control with the no communication atomic one. And when I validate this comparison, we can see that we have a set of errors, the same one that we had on the diagram, except that they come from real model validation, and they are here. And then the last piece of the approach, when we work with the situations, what the systems engineers would do would be to identify the situations of interest. So as they have always done, they do matrices with modes and states and relating them. So we can identify some specific situations of interest. So for example, here, I am going to focus on the situation where the satellite is in orbit, but we have no visibility towards the ground. I can express the situation here, and we see that in Capella. So I have a situation here which is in orbit and ground not visible. This is here. And for each of the modes, in orbit and ground not visible, we have associated configurations. I can try to request the result and then compare this expected configuration in orbit spacecraft control with the given situation that I just created. And in theory, I should have a similar result. I have issues when I compare an expected configuration and the situation. So this is what we have here. We can, for any expected configuration, we can specify the context, which is a list of situations of interest, and run the comparison, which is what I just showed in the tool. Then if we move in the logical architecture, we could perform the exact same approach. So I'm not going to describe that really precisely. I just want to mention that, of course, we would specify modes and state for each of the subsystems or each of the components and identify situations of interest and then try to understand what are the consequences of losing one specific component or losing another one. And if I go in the tool, and that will be the last part of the demonstration, I can open an architecture diagram in the logical architecture. Okay, and I can preview certain configurations. So for example, on Edmond component, I can display the failed configuration. And on radiation monitoring component, I can display another one that corresponds to the standby mode. So we see for each subsystem a specific configuration, and we see the impact that they have on the global functional chains that we expect from the system in its entirety. What I just talked about was mostly about predicting the behavior of the system in specific configurations. So what about parametric analysis? Non-functional properties that we would add to elements like components or functions, either through proper metamodel extensions or using property values like profiling on top of Capella, can be related to configurations. The computations that we would make could also be contextual to configurations. It's up to the developers or the providers of this extension to exploit the configuration mechanism to make their analysis contextual to configurations. So for example, the power consumption of a given component can vary in different modes, phases, or configurations. Resource requirements of a given component might vary according to the functions that it has to provide in a specific situation. Or the total mass or the power consumption of a launcher is different each time a stage rocket is detached. So all these different settings or contexts of the system can be expressed through configurations and situations, and performing non-functional analysis using situations and configurations can be really interesting. So we're reaching the end of this webinar. Where are we currently now? What are the next steps? So currently, what I've just presented here, all the tooling that I've presented here is a kind of incubation add-on to Capella. It's not yet part of the core of Capella. It will ultimately integrate the core, but we still need to have more return on experiment. There are some things that we still need to improve before it is promoted to the core of Capella. And this is a summary of the maturity of what I've presented. So we believe we are reasonably mature on the methodological approach. We would probably, it would be interesting to provide additional guidance for identifying the configurations. Sometimes it's not easy to understand what is a configuration, what is a mode, and what are capabilities, and how can I play with all these concepts, and so on. So a bit more guidance could be useful. We are reasonably mature on the concepts, configurations, and situations. We just realized that our current implementation of configurations is a bit too binary. So today, when I exclude two functions from one given configuration, it means all the other ones are included, and this is too strong of an assertion. So we need to have something that is a bit less binary, and we need to say, okay, all these elements of the models are not really relevant for this given configuration, so ignore them when you perform comparisons. We would probably need some kind of implicit rules, like when I'm defining a configuration by inclusion, if I include a function, I want all the parts of the functions to be included automatically, and I don't want to include manually each of the parts. So we can see that there are some implicit rules that should be provided, and the specification table should also be improved, because right now all what you see is crosses in cells, but the crosses don't have the same meaning if the configuration is defined by inclusion or by exclusion. So all these are ongoing developments. Preview of configuration in diagrams, we still have a little bit of work on that. So for example, if I have excluded a component exchange from a communication between two components, then the functional exchanges that are allocated to this component exchange could be automatically grayed. This is not the case today. So there are some automatic deductions that could be enriched. The side-by-side comparison of configuration is currently functional, but as you've seen, the ergonomics is really poor, because we kind of show the technical concepts of comparison situation that should actually just be part of the model validation and should be hidden by the tool. When we use the configurations for automated analysis, definition of situations is mature, but it would be good to have better ergonomics. So for example, assisted text. The computation rules need enhancements, and the fact that we will have really soon less binary configurations will help implement these computation rules. And the last one is what I said, like in this current version, all the technical elements required for the computations are made visible to the end user, which is not what we want. Any kind of help, should it be experimentation, funding, or contributions and so on, is welcome. This is, as I said in the beginning, this is an ongoing work. It is really promising because we've had some really good feedback from the people who started to use that. Any kind of help for the next phases is welcome. You can download this add-on and experiment. So here is the link. When you will download it, maybe there will be another build because it's pretty active at the moment. But don't hesitate to download. It's compatible with Capella 1.2, and just let us know what your remarks are and what your suggestions are and comments and so on in the forum. And I am done for today.
Why are you modeling mission phases as modes?
Oh. Why not? No, sometimes people do model them with capabilities, but we really understand them more like modes in the sense that there's only one phase at a time. There are transitions between the phases, and these are not things that come with capabilities. We can imagine that some capabilities of the system will be relevant only in one specific phase, but it's not necessarily a reason to have one capability per phase.
What do you think about defining the configuration with the capabilities?
We believe that this would be mixing concepts. For example, in a configuration, I'm specifying that an interface, a port, an exchange is not available. So I can go pretty deep in what I specify as available or not, and I don't want to establish these relationships with capabilities. What could be close to capabilities would be the expected configurations. The global expected configuration, the one we had on the left part of the diagram, that can be pretty close. But again, these kind of questions, it's exactly what I meant by the first line: additional guidance for the emergence of configuration or the definition of configuration versus modes, capabilities, and so on would be welcome. And even though we have ideas, we want these ideas to be backed up by operational feedbacks, and we have some already, but we would like to have more.
Okay, and maybe the last question for today. You mentioned as possible status: available, not relevant.
Yeah.
Oh, okay. Could you extend to more values? For example, started, start, not available.
Just do one more example. Hopefully it will help understand. I will remove the functional chains and I will activate the conflict detection, like mark elements with conflicts. The configuration, and I will select the no communication and the self-powered configuration. These two configurations have nothing in common. Like the self-powered configuration is only about these functions here. It just says that we don't have convert, we don't have store. The no communication is only about these ones. Like we don't have these communications functions. But when I specify that the self-powered excludes these two functions, I implicitly say that it includes all the other ones. And as the no communication specifies that these ones are excluded, it's interpreted as a conflict by the tool. And this is not exactly what we want. What we want is to say that, okay, this configuration is about these ones, And what happens elsewhere is not important, is not relevant for this configuration. And if we had that, then we wouldn't see any conflict when we display these two configurations. This is why we need something that is a little bit less binary than if it's excluded, then it's included, or vice versa. I don't know if that was clear enough, but
it was clear. Okay, you may have other questions, but we are running out of time.
So the forum is available, okay. And you have my email address.
Yeah. So don't hesitate to contact us.